Okay, color is one of those elements. It's a formal element of design that is a huge topic. And it's huge because it has so many issues that go along with it. Color is one of the first things we recognize about something that we're seeing. It's secondary only to the shape of that thing. And it has emotional, visual, and symbolic properties to it, so it's a very big deal. It is a visually dominant element. In other words, as I said, we will see it, recognize color of something fairly quickly. And it is a highly complicated element, and there's a whole separate course in color theory that if you haven't taken it, you will take it. And even then you won't have all the color knowledge that you'll end up needing throughout the course of your career. So it's a very vast topic and very exciting, and the right color can do wonders in a design. The wrong color can just totally blow things out of the water. So it's a really important thing. So we're introducing the idea of color with this lecture, and from here on your projects will deal with color issues. But this is not everything you will end up needing to know about color, so this is more of a whirlwind tour without going into a whole lot of depth. First thing to understand about color is that it is a perception. Color does not actually exist. We might see green leaves and white, daisies. But it's a matter of reflected light that is reaching our retina and sending impulses to the brain, and we're interpreting the color. But there is actually no color in an object. It's a matter of light waves, it's a matter of surface reflectance, and our ability to pick that up and see it, perceive it, understand it, and then know what to do with it. So color doesn't really exist. Color is a property of light, and without light we can't see color. So the first thing we need to begin with is a basic idea of light. If you regard light, whether it's sunlight, natural light therefore, or it's artificial light, you're not aware of light unless you're looking at the source or you're looking at the surface that's reflecting it. You can't see light waves, in other words. Light, what we know as white light, sunlight, what comes off an incandescent or a luminescent light bulb, is known as white light. It is the totality of all the possible colors. If we take light and refract it, which means bending it, it breaks apart into component hues. Hues are color families. And so we see things breaking apart and refracted into what we know as the rainbow. And they are in this order. There's a sequence to them. There's red, orange, yellow, green, blue, indigo, which is like a blue-violet, and then violet. And light exists on a spectrum. So there's red on one end, there's violet on the other, green's in the middle, and notice that there are various bandwidths. Some, like the yellow bandwidth, is very minimal, the orange is very minimal, the blue-green is minimal, the cyan is minimal. Pardon me, that was yellow-green, this is blue-green. But the visible light spectrum is a linear understanding. Light itself is actually part of the electromagnetic spectrum, which includes radio waves, microwaves, X-rays, gamma waves, things like that. And we understand light emanating from the source in waves, and wavelength determines the color. So red has different wavelengths than blue. And the length of the wave is determined from the very peak of the crest of the wave to the next peak. So this is one wavelength. Then there's the height of the wave, which is the amplitude. And so that determines the amount of light. If we've got really bright light, a lot of light, we have a high amplitude. If we have very low light, then we have a very low amplitude. So issues about color and light are wavelength and amplitude. So width, distance from the crest to the next crest, and then distance from the baseline to the top of the crest. So here's some examples. We have short wavelengths, somewhat of a low amplitude, long wavelengths, somewhat of a low amplitude. We have high amplitude short wavelengths, and notice the tallness of those waves, and then longer wavelengths, and again the tallness of the wave, the amplitude of the wave. So these would represent different amounts of light from low to high, and also different colors. The reason we see color on a surface is that we've got light coming from a source, and it hits a surface, and that light is either reflected or absorbed or both. And if all the light is reflected back by the surface, then it's white, because in light the total of all the color is white. If we have white light or visible light, and we're seeing blue on the surface, that means the red component and the green component are both being absorbed into the surface. And if we're seeing yellow, we've got white light, and the blue component's being absorbed, but both the red and the green are being reflected back at an equal or fairly equal amplitude. So wavelength and amplitude have a lot to do with the color that we see on a surface. The thing that's in the surface, now I mentioned before that there is no color on anything. Color is a perception. But there is something in a surface that's known as pigment. And pigment or colorant, this word here, are interchangeable terms. Pigment is the thing that provides the sense of color. It is the substance that reflects and absorbs the light waves. And anything that has color to it has pigment. If it doesn't have pigment, it's clear. So like a clear drinking glass would not have pigment, but a bottle of Coke has the kind of the greenish color in the glass. The glass is pigmented. Your sunglasses would be pigmented. Stained glass windows have pigment in them. So it's the pigment that creates the stage interacting with the light waves that actually gives us a sense of color when we're looking at something. So if something is clear, you know it has no pigment. Dealing with light, there's two types of light. One is direct and one is indirect. With direct light, we're talking about light that comes from a source that's like sunlight, light bulbs, your cell phone, your computer screen, things like that. It's the thing that is generating light. And there are two types of direct light, and the reason you need to know about these as designers is because different light qualities, because color is a property of light, cause us to see color in different ways under different lighting conditions. The same color will look very differently under incandescent light than it will under luminescent light, so it's important to understand the light quality. Incandescent light is created by anything that burns. So your basic tungsten bulb, which the U.S. government's trying to get rid of, it has that filament in it. It's a vacuum bulb. It has the filament. The filament's actually burning. And it creates a warm light quality. Candlelight, the light on your gas stove, the color of the flame on your gas stove, firelight, sunlight are all incandescent light sources. Luminescent light sources are those that are created through electronic, chemical, or biological means. Biological would be plankton or fireflies. Chemical would be something like neon, any sort of gas. It would be fluorescent tubes. It would be compact fluorescent light bulbs. It would be LED lights. And then electronic, of course, is your computer, your cell phone, your television screen, and so forth. Luminescent light has a natural coolness to it. So again, if you're looking at the same color under incandescent light, it will have a warm tone to it. The same color, again, will cool down under luminescent light. So that's direct light. Indirect light is that which is reflected from a surface. We've already talked about that a little bit, and that surface contains pigment, which is any substance capable of reflecting and absorbing light. So pigment is in food coloring, it's in fabric dyes, it's in Dunn Edwards paints, it's in the crayons, it's in the gouache that you'll be using. It's actually even in your graphite pencils and things like that. So pigment is a colorant or a substance that reflects and absorbs light. Used to be all pigments were natural. They were either mineral or dye-based, extracted from plants. Some were very expensive, like indigo, and certain kinds of scarlets and dark reds would be derived from plants, or grinding up certain color of beetles and things like that. Mineral-based come from generally earth, like cadmium and cobalt and things like that. These days we have synthetic colorants, and so we have color that is much more vivid. We have greater color capability in pigment because we can create it in the laboratory. So the quality of light, whether cool or warm, is going to affect how we perceive objects or the color of objects. And we're pretty much getting rid of actual film photography, but used to be, and actually still is in the digital realm. If you shoot a picture under a tungsten or a regular incandescent bulb, you're going to get a warm light quality. It's going to have a red-orange sensibility to it. If you shoot under fluorescent light, then you're going to have a bluish-greenish light quality, such as here. And then sunlight is what we consider balanced. And this is also true with digital. If you have a DSLR and you have the capability of shifting your white point, you can adjust for shooting indoors under tungsten, shooting indoors under fluorescent, shooting in sunlit shadows, shooting in direct sunlight, things like that. So those are all about light qualities. When we study color, we study it in a systematic manner, very similar to how we're studying aesthetic theory. There's a system, there's an order to things. Systematic study is quite useful in a variety of disciplines. It's very useful in the design realm because it leads you logically from one thing to another, and that's the approach that we're taking in this class. That's also how color understanding, color study is set up. There are basically two color systems. One is additive and one is subtractive. Additive deals with the realm of direct light, light from the original source. Sunlight, digital photography, film and video, anything that is computer generated, you're dealing in the medium of light. Even as you're looking at this lecture on your computer screen, you're dealing in the additive system. All the color that's created is created additively. Subtraction is anything that's printed, anything that is object-oriented or reflected light. So it pertains to reflected light. It's the more traditional understanding of red, yellow, blue in terms of primaries. Whereas additive is RGB, and that should spark some familiarity with some of you, at least. But most of us grew up with red, yellow, blue as the three primary hues, and with printing it's magenta, cyan, and yellow. Magenta is a red, cyan is a blue, and then yellow obviously is yellow. So CMYK still deals with the subtractive primaries. It's just real specific colors within those primary hues. Color has been studied systematically for centuries. And one of the reasons that there has been we'll say, a move to categorize and order color is because it is a very necessary thing in order to be able to work with it, to be able to apply it comfortably. And for the most part, the most popular color system is the Itten system, or the 12-hue system. Johannes Itten was a crony, a colleague of Joseph Albers, as part of the Bauhaus School. You can Google Itten and find out all about his color theory. And the thing is that his 12-hue system is the one that makes the most rational, reasonable, practical sense. There are other systems such as Ostwald and Munsell. There are the Goethe system and so forth. So people have studied color and categorized and so forth color for centuries, but the most practical system is the 12-hue system. When we're dealing with a 12-hue system, we're dealing with subtractive color. We're dealing in the realm of pigment. We're dealing in the realm of red, yellow, blue primaries. Within any hue system, you're going to have hues and you're going to have colors. And so we have to kind of clarify the difference between the two ideas. Obviously, we're studying color with this lecture. So color is the overall generic category of design element and topic for the day. In a 12-hue system, we have 12 hues. A hue is a color family. In a hue, you have thousands and thousands and thousands of possible color capabilities. So if we go to the red hue family, red is a hue. If we're talking about red and we're calling something red, then we have to say, well, which red is it? Is it magenta? Is it scarlet? Is it crimson? Is it cadmium red? Is it pink? Is it rose? So all of these are individual members of the color family, and they're the descriptive names, like puce. I still haven't figured out what puce is, but it is a color that exists somewhere. I've probably seen it many times without realizing it. But things like taupe and mauve and Swiss coffee, if you've ever painted your walls in Swiss coffee, those are descriptive color names, but every color belongs to a hue family. There's only 12 hues. Within the Itten system, there's categories of hues. We have our primaries, which are foundational hues that you cannot mix by putting any two colors together. You have to start with them, so they are absolutes. You can't mix a red. You can modify a red to be a little bit of a different red, but you can't mix a blue and a green to get a red, in other words, in pigment. So the 12-hue system, the primary hues are red, blue, and yellow. So pink is a primary color. It is a light red. So it is a primary color, but it's not a hue. The hue is the parent family. It's like the Smith family, and then you have Ed Smith and you have Sandy Smith. And Sandy and Ed are individual members of the Smith family. So the hue is the family name. It's like the last name or the surname. And then individual members are Ed and Sandy. So individual members of the red hue family would be crimson and magenta. Magenta, cyan, and yellow are the four-color process colors. And again, red, blue, yellow. So we haven't changed from this. We've just designated specific members of these hue families for the purposes of process printing. And when you study color theory, you'll understand why those work and why, say, cadmium red won't. If you mix two primaries together, you create a secondary. So there's three secondary hues. Orange is mixed from red and yellow, green is mixed from blue and yellow, and violet is mixed from red and blue. Now, because of wavelength changes, wavelengths themselves, and also because of the inability of pigments to mix perfectly, if you take a tablespoon of red and a tablespoon of yellow, you're not going to get orange, you're going to get a warm red. So understand that when you're mixing pigments, and this is true with inks, printing inks as well, they will not mix in direct proportion. It's a visual proportion. It's not an actual physical equal proportion. Tertiary hues, there's 6 of those, are made by mixing a primary with a secondary. So we have red-orange and red-violet. We have yellow-orange and yellow-green, and we have blue-green and blue-violet. And here's sort of the algebraic formulation if you're into algebraic formulations. So tertiaries are still hues. They're designated correctly, technically, by the name of the primary first. So it's not orange-red, it's red-orange. And red-orange is not the same as red or orange. It's a different hue family. Red-violet is not red, nor is it violet. It is a separate and distinct hue family. So we have 12 distinct hue families that are all created from the primaries. Black, white, and gray are colors, but they're not chromatic colors. They don't exist within hue families, but they're still kind of created from hue families in the subtractive, meaning the pigment or the reflected light system. So we have chromatic colors, we have achromatic colors, and it's a good thing to be able to tell the difference. But everything is derived from the hue families. If in the 12 hue system you would mix yellow with its direct polar opposite, violet, you'll get a really dark gray, what I call tar pit gray. It looks like the La Brea tar pit color. It's not true black, but it's a really dark gray, and it can be mistaken for black in certain situations. So if you can take 2 hues and mix them to that gray that has no hue or chroma whatsoever, it's just kind of tar pit color, you have complementary hues. So complements, and that's spelled with an E, very important because it's a balance, it's a completion, not a gee, you look great today. Complements will mix to an achromatic true neutral, a true gray. Complements side by side will enhance each other. So you take 2 colors that have a lot of chroma, which is a sense of having color, and you mix them together, and you will end up, if you mix correctly, a color that has no chroma, a color that is totally neutral. In the subtractive system, white is the absence of color, so the background for this page is white. We don't regard it as having color. Black is the sum of all color, or all chroma. The idea of black with light is you turn out the light and you have black. So black in the additive system, the direct light system, is the idea that there's no light. And then grays are midpoints between white and black. They are colors, but they're not chromatic colors. There's some schools of thought that say that they're not colors because they don't have hue, and that's true if that's the way you define it, but they are still colors because you mix them with chromatic colors and hues to create other colors. In other words, you take white as a pigment, mix it with red, and you're going to get various options of pink. You take black and you mix it with red, and you're going to get burgundy and maroon and things like that. A lot of colors are neutrals, but they have a sense of color or chroma to them. And you can get them by mixing complementary hues. Until you get to that true neutral right dead center in the circle, there are various steps that are taken toward that true neutral. In other words, if you start with red and you mix its complement green into it, the red will increasingly dull. It will increasingly become neutralized until finally it loses all sense of redness when you add more green. And if you add the right proportion of red and green, you'll get an achromatic gray, a true neutral. The idea of mixing complements before you get to the true neutral is that you have neutralized color, and these are generally known as earth tones. They're the browns, the tans, the mossy greens, the lake water blue, ocean green, things like that. Things that are have chroma but aren't really vivid and directly bright. They're not fully intense. This poster uses mostly earth tones. Value is a property of color, a characteristic of color. I've taken the hue circle and changed it to grayscale, taken all the chroma out, and so you can see the gray equivalents of yellow, of violet, of blue-green, of red-orange, yellow-green, and red-violet, and so forth. You can see that yellow is not as light as white, violet is not as dark as black. But the lightness and darkness, again, relates to the amplitude. Remember, we were talking on an earlier slide about the amplitude of the wavelength, the height of the wavelength. So value is related to that idea. Value is related to, obviously, the subtractive system. And it's the perceived lightness or darkness of color. Every color has value. Some colors are light, some colors are dark. We decrease value by adding white. We darken or, increase value by adding black. So this is 100% value. This is like 10% value. This is 0% value. Value in our perception is relative. This gray strip in the middle is all the same gray. It appears darker here because it's on a lighter background. It appears lighter here because it's on a darker background. So, but this gray is almost the same value as this gray right here. And it seems to lighten and have a nice gradient blend to it, but this is the same gray as this. Same thing happens with color. So we've taken a tinted violet, we've added white to the violet, and it's about the same value again as the gray strip above it. But you'll notice that that same violet, it looks lighter against the darker gray, against the black, and darker against the light gray. So value understanding changes our perception of color. Doesn't change what the pigment's doing or the light waves that are reflected. But value is a relative thing in terms of how we perceive it. You can take a darker color and make it appear lighter by putting it on a darker background, or you can darken it, or you can lighten it, darken it by putting it on a lighter background. Value contrast is a very crucial concept when you're dealing with aesthetic theory, when you're dealing with making aesthetics work to support the function of something. So many times, especially on websites, I see this a lot, that basically are designed without information. They're designed by uninformed people. You can't read them well because there's not enough value contrast or value difference between, say, the text and the background. Or you have something in the background that's a pattern and it's competing with the text. That's a value issue. The three ellipses are all the same value. They're the same degree of lightness. On a lighter ground, it's going to look darker. On a darker ground, it's going to look lighter. And on a ground that is just barely darker, it's going to look slightly lighter, darker than this one, but lighter than this one. But notice, especially if you squint, you kind of shut your eyes halfway, you're not going to be able to really pick out that ellipse very easily. This is the issue. When you have two colors that are the same value, they don't separate. You need value contrast, the difference between light and dark, in order to understand form. This relates to the Gestalt principle of irradiation and the recognition of figure ground. If you can't see a form or a shape against its background, you don't have good value contrast. Another thing about color is temperature. We have cool colors and warm colors. There are greater issues about temperature that when you take color theory you should be dealing with, but just on the basic level, there are hues that are considered cool and there are hues that are considered warm. Cool colors recede. In other words, they seem to retreat visually. Warm colors, warm hues, will advance. Given a cool and a warm next to each other, in our perception, the warm hue will be considered, be perceived as being closer in distance to us. So that's very important to understand. One of the reasons we can see McDonald's from far away, whereas we might not see a Daphne's, which is a blue and white color scheme. McDonald's has a warm hue and another warm hue, red and yellow, so that's meant for a reason. You can see them from a distance when you're driving down the road. So here we have a photograph that makes use of the cool and the warm. The warm facades of the buildings advance against the coolness of the sky, and they even actually advance before the kind of muted earth tone green of the water. And so the first thing we notice is the facade. It's basically, are we sitting there looking at a photograph or looking at a scene saying, okay, what's advancing and what's receding? No, we're not doing that. It's what you notice first. So if in a photograph or looking out the window, your eye goes to something, you notice it first. That's because it's going to be advancing because of warmth or coolness, or it's going to be pulling out of the background very distinctly. We use color to emphasize. We have a poster here for a design conference a few years ago, and obviously it's an orange and two different blues in the background, and then the white is the accent color. So the white, being without chroma and being much lighter in value, totally stands out from the highly chromatic background. So we use color to emphasize. And again, this is an issue, Gestalt issue of similarity. First of all, we have the similarity in chroma in the background, and then we have similar values. This blue is the same value as the orange. They're complementary colors. Then we have a shaded blue, which is a little darker, but it's hitting the smaller shapes mostly. So, but the chroma kind of blends together, and these are all a lot darker in value than the white. The white pops forward because it has no chroma, and it is light in value. It has no value. This is from a website. I think it was actually from MySpace a long time ago, but obviously we have black and white, and then we have, click here, the important stuff is using chromatic color. So we emphasize information with color. And obviously here our focus is drawn toward that red puzzle piece over the, kind of grayish white puzzle pieces because of the intensity, because it's darker, and that's the first thing we see. And if you squint your eye, seeing the little kind of mechanical guy holding that puzzle piece up, it's kind of hard to see. So we'll pick up in part 3 from here.